ring some bells as to what you guys did such a beautiful job of, good job by the way, of knocking out titration curves for a strong acid, strong base, and then a weak acid, strong base. So we did, earlier in part 8, we just recently did the chemistry behind a strong acid, strong base, so HCl and NaOH. And there's 3 points for every titration.
I don't know who that is.
Oh, that's normal.
Gotta be.
Huh?
That's like Nolan's song.
Because.
They said you were coming. Oh my goodness. Where was I? Oh my gosh. So there's always 3 parts to a titration curve, and the chemistry is going to look different depending upon what your heart, before the equivalence point, at the equivalence point, or beyond the equivalence point. The other thing that the chemistry is going to be different is what you're titrating. So let's see, let's work this problem. And right away, let's kind of get our bearings. Looks like what we're going to have in our beaker is going to be the acetic acid. So we're going to have 25.00 milliliters. I think I'll probably write this on the board because I'll be referring to it. CH3, COOH. I think we'll get through today. AQ. So that is our weak acid, and our strong base is sodium hydroxide. And any acid-base titration or acid-base reaction, you're going to end up with a salt, which is going to be sodium acetate.
Wait, any what you're going to end up with a salt?
Acid-base reaction. Any acid-base reaction, you're going to end up with a salt and water. So the original problem goes like this. We've got 25.00 milliliters of your weak acid. And of course, this is in your burette, so we're going to have various volumes of this. And the molar concentration is 0.100 molar, and kind of nice, 0.100 molar. So that's kind of the situation. And so usually you'd be like, you need to be able to knock out the equivalence point. And the fact that their molarities are the same and they react in the same ratio, does this make sense that I can actually say the equivalence point is going to be 25.00 milliliters for this particular titration? Okay. But actually here in a minute in part 8, well, more than a minute, but we're gonna do a calculation to come up with that equivalence point volume, because it's important, because before the equivalence point, at the equivalence point, beyond the equivalence point. So we're gonna do 3 different volumes. Not so surprising. We're gonna do one before the equivalence point, one at the equivalence point, one beyond the equivalence point. Okay, so we're gonna knock out what is gonna be the pH in those 3 regions. And it depends. We talked about, in part 7, we talked about preparing a buffered solution by taking weak acid and adding some strong base and basically converting some of that weak acid to its conjugate. So honestly, in the first region, that's what we have, a buffered solution. Specifically, we have some acetic acid remaining, and we have some acetate that's formed. That's region 1. That's always going to be the case when you're titrating weak acid with a strong base. So let's start there. So at this point, 20 milliliters, we know we're before the equivalence point, because equivalence point is 25 milliliters. And like I said, if we look at the chemistry, we have a buffered solution. So before the equivalence point, always in this sort of titration of a weak acid with a strong base, you have some of your weak acid left, and you have formed some of the conjugate base. So make sure we're all on the same page. There's my weak acid, and this guy right here is my conjugate base. I'll go ahead and put weak base. specifically CH3COO negative. Okay. So it's a buffered solution. So in order to find the pH before the equivalence point, guess what we're going to have to use? The Henderson-Hasselbalch equation. So according to the Henderson-Hasselbalch equation, it only applies to buffered solutions. The pH of the buffered solution will be equal to the pKa plus the log base 10, and you can either go molar concentration or moles. Always base in the top and acid in the bottom. Okay, so that's what we're going to have to use this time. They are kind of a pain in the butt sort of calculation. It's like counting beans. That's what I think of it. So we're going to have to see how many millimoles, we're going to stay in millimoles instead of go all the way to moles, did we have when we first started. So we're going to use this volume and this molarity to knock out the millimoles that were present first. 25.0 milliliters times 0.100 millimoles of CH3COOH per 1 milliliter. That will move the decimal place over. You're looking at 2.50 millimoles of CH3COOH started. So I think I'll go ahead and write that down. I don't know. Initial was 2.50 millimoles. All right. Well, we're at 20 milliliters of sodium hydroxide, so that's going to enter into the next step. At that point in the titration, we take our 20 milliliters of NaOH times its same molarity, 0.100 millimoles of NaOH per milliliter solution. Move the decimal place over, you're looking at 2.00 millimoles of NaOH that were present at that point. Again, the stoichiometry is nice and easy, so just eyeballing it, we know that, does it make sense? We're going to have a 0.5 millimole of our acetate left, and it looks like we're going to have what? 2 millimoles of your, sorry, a 0.5 millimole of your acetic acid left. And if you want to do it this way, you can. I think, though, probably that's going to be all used up, and we're going to have 2.00 millimoles of our acetate. And if we're good like that, remember that actually this can be moles of base to moles of acid. So I'm thinking we're getting down the road there pretty good. We just have to take these two guys, and plug it in, and we're almost done. But probably to do it according to Hoyle, because you don't know the stoichiometry is always going to be 1-to-1. We can come up with the millimoles of the millimoles of the acetic acid that's reacted. If we start with the millimoles of NaOH that were added, doing the stoichiometry of 1-to-1, that means that I'm going to subtract 2.00 moles. Okay, so 2.00 millimoles of CH3COOH was how much reacted with that 2.00 millimoles of NaOH. So by difference, we can get to kind of the conclusion I already had up there. If you take what you started with, 2.50, from that you subtract 2.00, which was how much reacted because you added sodium hydroxide, you're looking at 0.50 millimoles remaining. And one of the things I pointed out in the other titration problem that we did, don't get thrown off, because to come up with the molarity, I'm going to have to go with the total solution volume, which at this point in the titration is what, 45 milliliters. So here I'm at 20 milliliters of titrant. So 20 plus 25. So don't let that throw you off. Okay. But I don't think I'll need molarity, because I'm going to just put that into this form of the Henderson-Hasselbalch equation. So how much of its conjugate base form? Well, we can use stoichiometry. Start with 2.00 millimoles of NaOH that was dripped in. Again, we have that boring stoichiometry, 1 millimole of the conjugate base. CH3COO negative per over 1 millimole of NaOH from the stoichiometry. So yeah, and that's kind of why I kind of just jumped the gun and went over here and said we're going to have 2.00 millimoles of CH3COO. Yeah, that's right. The acetate ion that will be formed. Okay. So a few things here. Make sure you kind of know this has got to be a buffered solution because of the chemistry of what your of the weak acid and the strong base. So we can use this form of the Henderson-Hasselbalch equation, where the pH at that point in titration will be equal to the pKa times the log of the ratio of the moles of the base to the moles of the acid. And so I don't know, I don't know if we were given an original problem. We just need to come up with or you have to be given the Ka of your weak acid so you can knock out the pKa. We must have done this. It's like, where did this come from? We must have had this earlier in your notes. You have this earlier in your notes? If you take the negative log of the Ka, you should get 4.74 for acetic acid. pKa of acetic acid.
There's a table that I
Okay. Well, looks like I just kind of jump into that. I hope you guys know how to do that. I think you do. And then the log of the ratio of the moles, and it's always base over acid. So 2.00 millimoles of acetate ion over 0.50 millimoles of acetic acid remaining. 2 sig figs. So remember, when we get into the log function, we can show sig figs as trailing places after the decimal. So your pH at that point in titration will be 5.34. Okay, so that's 1 of 3. 2 of 3. So at this point, we're looking at now having 25 milliliters of titrant added, 25 milliliters of the base. And so at that point, we are at the equivalence point. And so looking at kind of the chemistry of what's going on, you figure the whole point of being at the equivalence point is all of this is used up. And this is what we have in the solution. And so here's where you have to look at what's driving the pH of what's left in the solution. And the answer is this guy right here. So the presence of that CH3COO negative is what's making it basic, not any NaOH. It's this guy right here because the NaOH is all gone. Okay? So we've done these problems before. It feels like forever ago. But we just need to then find the molar concentration of the acetate ion, CH3COO negative, and from that molar concentration, it's going to involve an ice table, which you're going to see here in the slides, and we're going to knock out the pH from actually, we're going to need to know it's Kb and all that. All right, so let's do a little bean counting. We need the molar concentration of acetate ion. So at that point, millimoles, we are going to basically confirm that these are all used up. The millimoles of sodium hydroxide at 25 milliliters look like this, 25.0 milliliters of titrant times the 0.100 millimoles of NaOH, 25.0 milliliters of titrant added times 0.100 millimoles of NaOH per 1 milliliter solution. So you're at 2.50 millimoles of NaOH have been added. And that's why we kind of make it's the equivalence point. I'm going to erase some of this other stuff. So the millimoles of the other reactant that has been used, we can, we're going to go with the 2.50 millimoles of NaOH. So stoichiometry is 1:1. So that means that 2.50 millimoles of acetic acid have reacted. So that's why you can count the beans, and that means that this is all gone, just like it needs to be at the equivalence point. Okay, so it's all gone. And I think we need to confirm that this is all gone. Maybe not. Okay. So I told you we need to, this is what's driving the pH of the solution. So we need to know what the molar concentration is of that acetate ion and then go from there for a pH. So counting beans again, and you guys would tell me, well, of course it's 2.50 millimoles just by looking at it. Well, let's kind of do the stoichiometry. At point of titration, we have 2.50 millimoles, sorry, 2.50 millimoles of NaOH. Stoichiometry is 1:1, millimoles of CH3COO negative to millimoles of NaOH. So yeah, we have 2.50 millimoles of CH3COO there. So in order to do the next step that we've done before to get a pH from the concentration of the, in this case, the weak base there, we cannot leave in millimoles, we gotta go to molarity. Sorry guys. So this is where you're gonna need to make sure you're gonna divide that number by 50. Okay, because in this point of the titration, we had our original 25.0 milliliter aliquot of acid, and now we have added 25.0 milliliters of base, so you're at 50.
So why, before we use the number of moles to get the pH, right?
Mm-hmm.
So we cannot do the same thing right now.
Nope, you cannot. Because we are actually going to, you'll see this here in a minute, but what's driving the pH is this. CH3COO negative plus water is in equilibrium. It's going to abscond onto a hydrogen and form acetic acid and leave the hydroxide ion. So that's what's making it basic. So actually we're going to have to do this sort of thing where to get to the molar concentration of the hydroxide ion, we're going to have to use a, I guess it's Kb, sorry. Kb is equal to molar concentration CH3COOH times the hydroxide ion divided by the acetate ion. Yeah, you cannot, this equilibrium constant expression only works with molar concentrations. It does not work with moles. Yeah, so otherwise, Henderson-Hasselbalch equation has that option. This does not. So the molar concentration is 0.0500 molar for acetate ion. Yay! I feel like some, my memory gets a little hazy here and there, but some semesters I think I just left it there and I haven't finished up the problem. But for y'all, we're going to finish up the problem. So we have to now do kind of something we did in part, it's either 3 or 5. I think it was part 5. What's the molar concentration of the acetate ion? I don't care about the sodium, it's a spectator. I do, but I don't. This will involve an ice table. That sounds like a threat. Okay, now here we go. This, if I was working this problem, I would definitely do like what I did on the board and you see on the slide. I would write out the equilibrium for the weak base, what it's doing chemistry-wise. CH3COOH, CH3COO negative, the acetate ion will interact with water this way to form acetic acid and a hydroxide ion. And then we, from there, come up with the Kb expression, and it's all of our equilibrium constant expressions take the same form, where it's the molar concentration of the products divided by the molar concentration of the reactants raised to their stoichiometric coefficients. Kb is given 5.6 times 10 to the negative 10th. And this, I think, is back in our notes because we did a lot with acetic acid, so we knocked out the Kb earlier. So just to kind of remind you how this goes. Oh, this is showing you how we got Kb. So we actually got Kb for acetate from the Ka for acetic acid, recognizing that they are a conjugate acid-base pair, and so the Kb will be equal to Kw divided by Ka.
So I guess, like, for finding the Kb, K is going to be given?
Well, it depends. Like, since acetic acid is stronger than acetate, acid and base-wise, it's been given, the Ka is given. But another common example that we've looked at before is NH3, which is a good proton acceptor, so actually it's a weak base. And in this case, since that's stronger than this is, you're going to be given a Kb. So it kind of depends on how the strength of your conjugate acid and base in that pair. Whichever one's stronger, you get.
So it's just up to you to determine whether you need Kb or Ka.
Yeah, it depends on how it's working in your problem as to know which one you need to use. Yeah, in this case, we're using Kb because actually it's the weak base that's driving the chemistry. If it was the weak acid driving the chemistry, this would have been a Ka expression.
Right.
So, Yep. So, of course, you divide that out 2 sig figs, and that was that 5.6 times 10 to the negative 10th you saw a minute ago. Okay, here's our ice table. And if we this seems like so long ago when we did these, that's how I feel. If we let X be equal to the amount of the acetate that interacts or hydrolyzes your water, okay, then it ends up looking like this, where initially we have 0.0500 molar acetate and 0 molar of the acetic acid and the hydroxide ion. Again, we know we have some hydroxide ion because water just breaks apart to a certain extent, but common ion effect, it works pretty good. And then our changes will be negative X plus X plus X. So at equilibrium, you're looking at a concentration of your acetate ion remaining will be 0.0500 minus X. Concentration of your acetic acid formed and your hydroxide formed will both be X. So if we take those quantities and substitute it back into our Kb expression, it looks kind of ugly. Basically, X times X in the numerator and 0.0500 minus X in the denominator is equal to Kb. And we said that we can apply a simplifying assumption. If the amount of this that hydrolyzes is relatively low compared to the molar concentration that it started out with, and to kind of put that mathematically, we're saying X is significantly less than 0.0500. If that's the case, then this quantity in the denominator, if that's pretty small compared to that, then actually that becomes 0.0500. Okay? So life becomes a lot simpler. This thing in red, just copied and pasted from an earlier slide when we did this, rule of thumb is about 100. So what you do is you take, in this case, your Kb times 100, and that the molar concentration of your weak base, in this case the acetate ion, needs to be greater than that. So what we have, 5.6 times 10 to the minus 10. So 5.6 times 10 to the negative 8. So anytime that your molar concentration of the acetate ion is greater than that, you're pretty good. Unless you're using online homework. Then it gets mad at you. Okay. So if we apply the simplifying assumption, then the KB expression simply becomes x squared divided by 0.0500 is equal to KB, which is 5.6 times 10 to the negative 10th. Yay! So we're going to kind of crisscross multiply and take the square root. So x is the square root of 2.8 times 10 to the negative 11. 2 sig figs. Well, I gave myself 3, but I'm thinking it should just been 2. 3 sig figs, and x is 5.29 times 10 negative 6. And if you look back at what x means, then we're going to hone in on the hydroxide ion concentration to see what our pH is. So according to our ICE table, then the molar concentration of the hydroxide ion is 5.29 times 10 to the negative 6. This seems like so long ago when we said we can get to the pH using this information. I can't remember how we do it. There's a couple different ways to go. Looks like I'm going for the POH. So the POH will be equal to negative log of 5.29 times 10 negative 6. And that's equal to 5.28. Hopefully you feel kind of comfortable with going from POH to pH. You add them together, and at 25 degrees Celsius, they need to be equal to 14.00. So the pH is equal to 14.00 minus the POH, which is 5.28. And you're looking at 8.72 is the pH. A lot of work goes into that one little problem at the equivalence point. Really? I think, anyway. I guess welcome to chemistry. To think through all that's going on. So I think for the last one, I think I bail on it. I basically say in Wednesday's lecture, we looked at a strong acid instead of a weak acid being titrated with a strong base. And actually at this point, it's the same chemistry that's going on. At 30 milliliters of sodium hydroxide, basically you have annihilated all of your acetic acid, and the only thing that's making it something other than neutral is your excess hydroxide ion that's present because of your the OH from your NaOH. Okay, so it's just that. We could we would do the math. Come up with how many millimoles would be what, 3.00 millimoles of NaOH at 30 milliliters of solution. Recognize your 0.5 millimoles of NaOH excess. Divide that by the total solution volume to get the molarity of the hydroxide ion. So it's just the same as we did for the HCl titration. This is kind of like tabular data of what you guys did yesterday in the lab, where the last column actually is the pH of the solution as you add this volume of sodium hydroxide. This is kind of a curve. Well, this curve goes along with the data you saw on the previous slide, where along the x-axis we have volume of titrant, volume of NaOH added, and along the y-axis we have the pH. And hopefully you can kind of see this sort of draggy sort of as characteristic of a weak acid strong base titration. Equivalence point here at 8.72 according to the number we crunched. So question number 4 on your calculations for the second part of your lab yesterday went something like this: half neutralization point. And you would tell your uncle how to do that. So you're set. Okay. So basically, no pun intended, when you have just kind of draw the titration curve like was on the board yesterday. This is volume of titrant. which in this case is NaOH, and this is pH. And you kind of have this slopey, and then you have kind of a nice, and this was our equivalence point, and this was like our equivalence volume. So at this point, halfway, so half neutralization point, I can't spell neutralization point, can't spell neutralization, okay? So at this point, basically, how do I say this? I think it's maybe on there. The amount of your acid, half of your acid's been used up. So if we have CH3COOH plus OH minus goes to form CH3COO negative plus water. So basically you have half of this that you started with, and you have half of this on the way to its neutralization point. So if I take the ratio of the moles of base to the moles of acid, they're actually going to be the same. 1/2 divided by 1/2 is 1. So in my Henderson-Hasselbalch equation, this ratio becomes 1, and the log of 1 is 0. Yep. So that becomes 0, and in that case, at that sweet place, if we go up and see what the pH is, that actually is going to be equal to pKa. That's how it works. So it's a nice little acid base, it's a nice little buffered solution that you've created. So, yeah. So half neutralization point, the pH is equal to the pKa. So this is my little kind of making sure we are all on the same page with regard to finding that tipping point, what we call the neutralization point. You could be faced with something like this, where, remember in Chem 1, what I like to do is take the information from the problem and kind of put it underneath the species. So the acetic acid, CH3COOH, we know that the volume is 35.0 milliliters, and we know that the molarity is 0.108 molar. Seems like so long ago when we were doing these. We know something about the sodium hydroxide. We know that the sodium hydroxide looks like it is 0.235 molar, question mark volume, basically, if you read that a few times. So we can use and I think I've got it on my slides coming up, we can use the volume and molarity to get to moles of acetic acid, use stoichiometry to get to moles of sodium hydroxide. Once we have moles of sodium hydroxide, we can use those moles and molarity to get to volume. I think I do. So here we go. We know the most about the acetic acid. Take that 35.0 milliliters of solution, using the molarity to get to, actually we're going to go with millimoles though. We're not going to go to moles. So here's the molarity, 0.108 millimoles of CH3COOH over 1 milliliter solution. I can't do that one in my head. 3 sig figs, you're looking at 3.78 millimoles of CH3COOH. The next stop is to use the stoichiometry to get to millimoles of NaOH. And it looks like this. From the balanced equation, we know they react in a 1-to-1 ratio. So if we take our 3.78 millimoles of CH3COOH times 1 millimole of NaOH over 1 millimole of CH3COOH, millimoles of CH3COOH will cancel. We have millimoles of NaOH, which I can do that math in my head. 3.78 millimoles of NaOH. And now in this case, we're after volume. So we're going to use that and molarity to get to volume. So here we go. 3.78 millimoles of NaOH over 1. And we're going to use the flipped version of the molarity of the NaOH. So it looks like this. 1 milliliter of solution, of the NaOH solution, in the top per 0.235 millimoles of NaOH. So millimoles of NaOH cancel. We're left with milliliters of solution, 3 sig figs, and you're looking at 16.1 milliliters of solution. So just to make sure we're all on the same page, it's possible that you might need to identify the equivalent volume so you know where you're at in titration. So with this example of a weak acid being titrated with a strong base, if I'm before 16.1 milliliters of solution, I'm talking buffered solution, Henderson-Hasselbalch equation. If I'm at 16.1 milliliters of titrant, I'm talking, I'm going to need a high stable because I basically converted all of my weak acid to its conjugate base. Beyond, it's just pH is driven by the excess NaOH. Okay, so this is kind of an interesting little thought. Other titration curves. Strong acid, strong base. But the trick here is it's like, if you look at it, you're like, that's not what we did, or that's not what ours looked like. And what happens is it's starting out basic and ending up acidic. So all this is basically taking what was in your burette, making it your analyte, and taking what was an analyte, making your titrant. So this would be titrating what? A strong base with a strong acid. Okay, so it would look like this, but it kind of has the same nice sharp kind of plateaus. Weak base titrated with a strong acid. You should see kind of a wimpy sort of slopey sort of thing. In this case, the weak base that was chosen actually was NH3, and it's titrated with HCl. What you guys are doing with your data are kind of looking for that snap inflection point. You're showing it here at an equivalence volume of about 40 milliliters. There's your pH of the solution at the equivalence point. So before the equivalence point, buffered solution. After at the equivalence point, it's driven by the formation of this NH4+, H conjugate acid. Polyprotic acid, you have a couple of bumps. So H3PO4, phosphoric acid, actually you should have kind of, I think we're only kicking off 2 protons here. But you can kind of see the first proton being kicked off here and the second proton being kicked off here. Indicators. So the indicator you pick, so we've used one indicator, by the way. So if we find a pH of 7, you go up to see what's good for a pH of 7. Well, not real good for a pH of 7, but you guys have used phenolphthalein, which it works okay as long as it worked okay for us. But whatever your the pH of your equivalence point is, you're going to want to pick something that changes color there. Well, put it this way, you guys used red cabbage. Guess what? Red cabbage has a lot of different possibilities with regard to the color it can form at the different pHs. Some color indicators only have 2 colors, not like red cabbage. These would be kind of examples of those. Let's see. Acid, tetracene, hydroxide. Oh. This is actually kind of putting on one plot the 2 things that you guys did. One is HCl, the orange one's HCl, and kind of this purple one is acetic acid. So this is your first titration, this is your second titration. Okay, notice that they kind of, like I said a minute ago, they end similarly, okay, but they start out different. In the case of the type, just go right to the weak acid. Here in this region right here, you actually are making a buffered solution. So, all right, dun, dun, dun. 5 minutes left. So, any questions about homework? All right. You got the deal. So Monday we'll start Unit 5 and take some for the road. So like I can never clementines or mandarins. I mean I